It's great to be here. Thanks to all of you for joining us this morning. I am a climate scientist at the Lamont Doherty Earth Observatory and have been working for many years to study climate change over many different timescales and globally. I also work as co-director of the undergraduate program in sustainable development and through a chair position on the Earth Institute Education Committee, also oversee many of the Earth Institute programs within the Earth Institute. So that's how I come into this discussion. I am not an active K through 12 educator, although I do a lot of these kinds of things in speaking with teachers in the New York City area. But I always learn every time I do one of these, and so I really do hope that we can have a discussion as much as anything throughout the course of the presentation. I really don't care if I only get through 2 slides. I think that this is most effective if you do ask questions throughout. We certainly can have time at the end, but I encourage you to post questions in the Q&A, and I will do my best to address them throughout the talk when I think it's most effective. I don't have my chat window open. If I have too many windows open, I can't see my presentation. So I do have my Q&A window open. I'll try to keep track of that, but that seems like the place to specifically put in your questions. Okay, so as far as just an overview of my plans, I'm going to take, as the initial presenter, I'm going to take a fairly large view of this problem and kind of give you the Cliff Notes version of what I see the 3 important facts about climate change to be. And in the second half of my talk, what I hope to do is talk a little bit about impacts, but in particular how I see the opportunity for connecting with 6 through 12 grade students in this issue. And so I hope that's how we can have a discussion in the second half. I just want to begin by going through a few important facts, and I'm going to start with the punchline. The Earth is warming and we're causing it. This is not a controversial scientific statement, and I really see 3 important supporting facts that contribute to how we know this. So what I'm going to do is step through each of those principal facts. The first is that CO2 in the atmosphere is increasing. And there are some basic observations that confirm this to be the case. Before I do that, though, I do like to kind of go through a quick scaling argument. Some of you may have seen this, but for those people who have a hard time imagining human activities to perturb something as large as the atmosphere, I think it's important to keep in mind how small or how in mass and size the atmosphere actually is in the Earth system. So if the Earth were a basketball, the atmosphere would be about 3 pages of paper thick. If we instead do the scaling by mass and we make the Earth about the size of an average car, the mass of the atmosphere would be about a paperclip. And so when we think about it in those terms and we think about human activities in the context of that, it might become a little bit easier to imagine how our activities could perturb something like the atmosphere in the Earth system. Okay, so we actually do have direct observations of CO2 in the atmosphere. This is the famous Keeling curve that started in the late 1950s and continues up through present day. Just to give you a few sort of number points along the way, this record when it was originally began collecting was about 316 parts per million. Parts per million makes CO2 a trace gas in the atmosphere. That's about 0.0316% CO2 in the atmosphere, but because CO2 is radiatively active, it's a very important greenhouse gas in our atmosphere. When I was born in the late 1970s, the record was around 330 parts per million. Last year, it was 411 parts per million, and the average of June, which is the most complete month in the record, was 416 parts per million. As far as where CO2 was prior to the Industrial Revolution, it was pretty steady over the last several thousand years at about 280 parts per million. So we've seen over a 40% increase since the beginning of the Industrial Revolution and over a 30% increase since this record began in 1959. The other analogy I like to make, so we're at about 0.04% CO2 in the atmosphere. If you have any doubts about whether or not something small like that can influence a larger system, I always like to point out that if a person like me drinks 2 beers, my blood alcohol content is about 0.4%. And that's the point at which the body just begins to feel the effects of alcohol. And while the human body and the earth system are two very different systems, it's another example of where trace amounts of a substance actually do have large impacts on the operating of a much larger system. So CO2 is increasing certainly over the last 60 to 70 years that we've been monitoring this. But we also know that it's varied at different levels into the past. And one of the records that we have for estimating CO2 in the past is from ice cores. These are taken from the ice caps in Greenland and Antarctica. You can see an example of a scientist holding one in the picture. There are small, tiny bubbles trapped in those ice cores. And from those bubbles that represent little samples of the atmosphere when they were formed, scientists can infer what past concentrations of CO2 were when those bubbles were formed. So this particular record goes back 800,000 years. It's a record taken from Antarctica. And what you can see in the inset is that CO2 has varied between about 180 and 300 parts per million over the last 800,000 years. The maximum amount during an interglacial period about 350,000 years ago was 300 parts per million. So the take home here is that sitting at just over 400 parts per million presently puts us well above anything that we've seen in the last 800,000 years. If we actually want to find out when CO2 in the atmosphere was at 400 parts per million in the past, we have to go back 3.5 million years ago during the mid-Pliocene. So we have been at this level of CO2 in the atmosphere, but you have to go back a long time. And the Earth was a very different place during that period. Just to put that time expanse in context, I've included another number at the bottom of this slide, which is the amount of time that the Homo sapien species has existed. So we've been around for roughly 200,000 years. And so at our present level of 400 parts per million, no human in our history, in the history of our species, has existed during CO2 levels currently. As an interesting, or I guess personal aside, my kids were born over the last several years, both of whom were born at levels above 400 parts per million, and they will likely never live during a time period that is below 400 parts per million. And so their lifetimes will be very different than all of the Homo sapiens who have lived prior to this time period. So I think I hope I've established the fact that CO2 in the atmosphere is increasing. The second fact that I want to go through is that the Earth is warming. So we again have lots of records of temperature on our planet. We have direct observations of temperature from meteorological stations and ship-based observations going back to the mid-1800s. So this particular record was developed by NASA GISS, which is an affiliate of Columbia University here in New York City. And what this record is showing is average global temperature beginning in 1880 and continuing up through present day. A few things to note about this record. If this was a stock price, I think we could all agree that the price of the stock was going up. As temperature, it is indeed increasing. In fact, over the length of this record, the overall temperature increase has been about a degree Celsius of warming. The years that I've listed along the right side of this panel are the top 10 warmest years. And you can tell this from the time series, but you can also see in the years here, the top 10 warmest years have all been in the 21st century. So that's something that you would certainly expect of an increasing time series like this. And again, just to put this in context of lifetimes, most kids that have been born in the 21st century will live in a mean climate, or have lived in a mean climate to this point, that is warmer than any time during the 20th century. So by our direct observations, temperatures are increasing. And 1 degree C might not sound like a lot, but I want to put that in a slightly different context through an analogy. So if you look at the ups and downs of this record relative to the long-term change, that long-term change in global temperature is quite a significant amount. And if we exchange the ups and downs in time for our experience with ups and downs of height, we can actually make an analogy to what that 1 degree C increase would look like if there was an equivalent proportional change in human height. So this is just a calculation that I've done showing that that increase in temperature amounts to a similar increase in human height of about a foot in both women and men in the United States. So it may be hard to perceive a 1 degree C global temperature change, but I can guarantee you that we would all notice if suddenly everyone around us was walking around a foot taller than our experiences. So this is a significant temperature change that's been observed globally and is a robust feature of the observational record that we have. But if you don't like surface air temperatures, there's lots of other things in the climate system, and I don't have a time to go through all of it, but the point I would like to make is that global warming is fundamentally an increase of temperature in our planetary system. And if you begin with the hypothesis that that increase in temperature is causing warming throughout the Earth system, there are lots of indicators that are consistent with this hypothesis. So in addition to surface temperatures increasing, we're seeing the cryosphere diminish in terms of the amount of snow cover that we see from year to year. We're seeing ice volume diminish in glaciers and ice sheets. Water vapor is increasing in the atmosphere, which is consistent with a warming atmosphere. The oceans are warming, sea level is increasing, which is consistent with a warming ocean and just thermal expansion of the ocean, in addition to all of the additional fresh water that's being dumped into the ocean due to the melting cryosphere. We're seeing sea ice melt. All of these things are very consistent with a planetary warming that's happening as a consequence of increasing CO2. So I've jumped the gun a little bit because what I want to talk about as the last fact is that increasing CO2 is causing the warming. So this really takes up the causal mechanism. We've established, I hope that we've established, or we certainly established beyond what I've shown you, that the Earth is warming and that CO2 is increasing. Now let's look at just a few of the pieces of evidence that connect the increasing CO2 to the rising temperatures. What I first want to say is that this isn't a new finding within the scientific community. In fact, scientists have been studying how planetary temperatures are set for well over 100 years. And this is an example of some of the original scientists who really start to put the pieces together regarding the influence of CO2 on the Earth's temperature. So you may recognize Fourier and Arrhenius. Eunice Newton-Foote might not be as familiar to you, but she was actually hidden in the annals of history for a long time, but about in the last 10 years, scientists have realized through some early work that she published in some obscure journals that she was actually one of the first scientists to connect solar energy and the responses of CO2 in the atmosphere. And so all of these scientists, if you just look at the titles of these papers that I've included, Fourier's original paper on the temperatures of the terrestrial sphere and interplanetary space, Foote's article, Circumstances Affecting the Heat of the Sun's Rays, and Arrhenius, who actually was the first to devise a fairly simple climate model, did that in this paper on the influence of carbonic acid, or CO2, in the air upon the temperature of the ground. So since the 19th century, scientists have been talking about this. It's not some new discovery that is unvetted, but in fact, our understanding of the connection between CO2 and planetary temperatures is well over 150 years old, and something that is a long process of scientific thought and discovery that goes back a long time. So we already have, just based on the theory and the established science, well-established theory and data that would suggest if we increase CO2 in the atmosphere, the causal effect would be that the planetary temperatures would increase. We also have a lot of data that comes from various observations. I'm going to just show one, which is that ice core record again. And I've already shown you the CO2 going back 800,000 years from that ice core record. But now I've added an additional curve representative of the temperature over that time period as well. So CO2 is in light blue, temperature is in the dark blue. And they get the temperature from these ice core records by looking at the isotopes in the ice core layers. But the point of this figure is simply that CO2 and temperature mark in lockstep over this last 800,000 year period. So there is also indication through records like this that CO2 and temperature are tightly coupled on the planet and they go hand in hand. So again, additional evidence that goes back a long time in terms of our study of the planet, indicating that these two things are connected. So the last thing that I want to show, however, is another important means for which we study the planet, which is through climate models. And climate models are, at their foundation, computer code that divides the world into three-dimensional cubes. And within each of those cubes represents the physics and chemistry as we understand it within the planetary system. So again, this builds on decades of work to understand the processes in the climate system and to represent them mathematically through the physical and chemical relationships that define them. But you could think of them as big physical accounting machines that move energy and mass and momentum around within the Earth system, given the governing physical laws as we understand them. And what's important about climate models is, first of all, they're not perfect and they're being refined all the time. But what the advantage they give us is to essentially run control experiments. We, of course, can't run control experiments with the Earth system. It's too large and it's just not possible, or would it be wise? We are, in fact, running a giant experiment currently by dumping a ton of CO2 into the atmosphere, but we can't create a counterfactual world in which we don't dump that CO2 into the atmosphere and see what happens to the Earth system. The only way that we can do that is with a climate model. And so it's akin to the classic experiments that we're all familiar with regarding, for instance, plants. This is just an example of a type of compost that is added to these plants that is apparently detrimental to their growth. You can see the control on the left, and then various amounts of this substance that's added to these plants. We can do the same thing with climate models to try to piece out the causal impacts on the climate system and this warming over the last 150 years. So what I'm going to do is show you an animation, and it's going to swipe different colored lines over this plot. The time series that you can see is the observed temperature time series that I've already shown you, going back to 1880. And this animation is going to start, and it's going to first show you model simulations using only natural factors in the climate system. Those natural factors are the natural features that we know to affect climate, like volcanoes and solar variability and orbital orientation. And then it's going to do the same simulations, but using only the human activity, so increases in CO2, aerosols. And what you'll see as it begins, I'm going to start it now, what you'll see is that each of these factors matches well or poorly the observed temperature record. And as far as the natural factors go, you can see that they don't come anywhere near influencing the global temperature in the climate models in a way that allows the global temperature to warm, particularly in the later half of the 20th century. So you can see all of those natural factors here, and they don't do anything to reproduce this warming trend in the later part of the century. Now we're beginning the anthropogenic influences. And these influences both warm and cool the planet. So you'll see aerosols here actually have a cooling effect on global temperatures. And now you'll see the greenhouse gases influencing temperatures by causing them to warm. And what we'll see collectively now is all of the human factors and how they go together to match much more closely that observed temperature record. But now when we put the human factors and the natural factors together, you'll see that the climate models do their best at matching the observed temperature record. So first of all, there's lots going on. There's human factors and natural factors that cause climate to change. But the take home here is that within the climate models, as we represent the climate, the only way that we can reproduce the observed temperatures and that rapid warming over the last half a century or more is to include the human factors. And so this is an important causal connection within our climate modeling experiments that show the human activities to have a very important role in the warming as it's been observed over the last 150 years. So that brings us back to my original statement: the Earth is warming and we are causing it. This has been a quick flyby assessment of what I see as the three fundamental facts that really establish the warming of the Earth's surface and planet and what's causing it, which is the increasing greenhouse gases from human activities that are contributing the most to that warming. But you don't have to take my word for it. This is a paper which actually looks at consensus on the statement that I showed you, whether or not the Earth is warming and whether or not it's caused by humans. And the title of this slide is actually the title of the paper, which is one of my favorites, although it's a mouthful. Consensus on Consensus, a synthesis of consensus estimates on human-caused global warming. But what this slide is showing is each of these pie charts is a different assessment of the scientific consensus on human-caused global warming. And first of all those percentages for each of these studies is above 90%. And when you start to break down the scientific communities and you start looking at, so there's a lot of these assessments have been done across scientific communities, regardless of discipline. But what you find in a lot of these studies is you get closer and closer to climate scientists specifically, the people who are studying this problem most directly, that percentage goes up. And in general, the sort of rule of thumb number is that there's more than a 97% consensus within the scientific community that the Earth is warming, we're causing it. So while this may be represented as up for debate, or I'm sure that all of you have seen talking heads who say that this is not something that is resolved. Within the scientific community, this is about as close to a universal consensus as you can get. And let me tell you, as a scientist, we tend to be a prickly bunch. It's not easy to get us to agree on many things. And so this consensus is significant given the, I think, nature of most scientists who like to pull at unestablished or pull on the pieces of theories that are open for debate. Okay, so with that as context, I want to make just a few more points. What I've shown you is historical observations. Certainly we talk a lot about where we're going, but I think more and more we're recognizing that the impacts of climate change are here and we see them all around us. I don't have time to go through all those things, but I think this is a valuable slide. This is showing the cost in billions of dollars due to natural disasters in the United States beginning in the 1980s. The colors are for different kinds of natural disasters. Generally, you see that those disasters are increasing. So the number of events are increasing. Of course, the cost of all of those events are increasing. But it's also worth looking at which things are increasing. So you can see an increase in the number of green events, which are severe storms or tropical cyclones or wildfires. What's decreasing is things like winter storms and freeze events that are consistent with the fact that things are warming, and we're really increasing the kind of warm extremes, drought, wildfire, heat waves, severe storms, flooding. Those are the increasing events that we're seeing more and more. And those are the events that we expect to increase and cause additional challenges moving forward from here. Okay, so with that perspective on things being here, I do think it's worth thinking a little bit about the future and considering what the future holds. And I've put Newton's second law in the crystal ball because what we have for doing that is the established science around our understanding of how the climate system works and unfolds. And there's uncertainties associated with that. It's not a perfect understanding. But when we think about the future, the biggest uncertainties actually have to do with socioeconomic factors and decisions that we ultimately will make as humans. So questions like how we will generate energy in the future, how we will use that energy in the future, how cities and countries will continue to modernize and develop into the future, and what our population size will look like in the future. Those are all uncertain future unknowns. And so what we tend to do in thinking about what the future will look like is create scenarios. So what I'm showing you here on the left is the observational temperature record from 1900 up through present day that I've already shown you. And the colored lines here into the future go up through 2100, and they represent different scenarios for how we might evolve into the future, what kind of decisions we might make into the future. And what I want to highlight here is, first of all, given the scenario, the kind of projected warming is anywhere between 0.3 of a degree C and upwards of about 5 degrees C. But there's other important things to note in this figure. So each of these colors are different scenarios. There's shading around each of the colors. And that represents the spread associated with the different climate models that we use to run these scenarios into the future. So you can think of that really as a scientific uncertainty. The things that we don't know as represented in the way that different climate models simulate what a future climate will be under these different scenarios that we feed into them. But the much larger uncertainty here is what I call decision uncertainty, and that's the expanse of this span, which represents the different scenarios into the future. So the key here is that the scientific uncertainty is not something to dismiss, but it's by far much smaller than the range of decision uncertainty that relies really on what we do into the future that's important. I do want to point out, this is sort of an aggressive mitigation scenario along the bottom. This has been called the business as usual path into the future. Some have argued that it's more appropriate to think about it as a worst case scenario, but I will be referring to this as a worst case scenario into the future in some of the things that I show you from here. So just to put that worst case scenario warming in context, I think it's useful again to think in terms of some scaling. This is the Manhattan skyline. The Freedom Tower in front is about 546 meters tall to the top of the antenna. The last glacial maximum about 20,000 years ago was about 5 degrees cooler than present day. And Manhattan was actually the terminus of the Laurentide ice sheet at that time. And ice at the end of Manhattan Island was probably not as tall as the Freedom Tower, but it's estimated to have been a couple hundred feet high. So perhaps the height of some of these other buildings in the foreground here. Point being that the difference between present day and 5 degrees of cooling is ice on Manhattan Island reaching several hundred meters above sea level. And we're talking about an ice age of warming into the future. So again, in thinking about, is 4 to 5 degrees C of global temperature change significant? Well, it's the difference between an ice age and where we are presently in an interglacial in the cooling direction. And we can expect similar magnitude change into the future as we warm 4 to 5 degrees. So an ice age in the opposite direction. The other point that I want to make that's really important about this temperature change is that when we look at the rate of temperature change that we're projecting, say through the end of this century, it's massive compared to most of the change that we've seen in Earth history. It's happening much, much faster. And again, to sort of put it in perspective, that ice that was on Manhattan Island melted over the course of, let's say, several thousand years. And if we look at how fast that was and scale it to you or I walking down the street, the rate of change that we're projecting to the end of 2100 through this worst case scenario is like being passed as a pedestrian by a car going 160 to 300 miles per hour. So it's incredibly rapid. And the reason why that matters is because the rate of change is important for all living things' ability to adapt. So both from the perspective of our species and our ability to adapt to the changes that are coming, as well as ecosystems as a whole and species' ability to respond to this change. And we're already seeing, because we're already experiencing quite rapid changing, significant changes in ecosystems, biodiversity losses that aren't exclusively tied to climate change, but it's certainly exacerbating some of the additional pressures that are on species currently and really contributing to the severe biodiversity losses that are another feature of our current Earth system. The last thing I want to say about this is that 2100, at least when I started doing this, seemed like a long ways away. It doesn't seem as far now, but in the context of a human lifetime, it's actually pretty close. So children being born today, given current life expectancies, will likely live to 2100. So we're within a human lifetime, indicating that people being brought into the world today may experience these kinds of changes. And so it's not that far away in the context of our own thinking. Okay, so just a few more things about these temperature changes. I think it's important to recognize that as temperatures increase, mean temperature is one thing, but there's a lot of risks that go along with that. And as temperatures increase, the number of risks increase, and the severity of those risks or the events associated with those risks also increase. And that's an important thing to keep in mind. So as we try to reduce the amount of warming into the future, we're also reducing risk and our exposure to that risk as we hold temperatures down as best we can. It's important to recognize that these risks are systemic. So it's not just about the physical climate, but there are risks tied to migration, food, public health, education. It turns out that we all learn more poorly when temperatures are at higher levels. And so this means significant things for developing nations and the ability of their populations to learn. Conflict, economics, infrastructure, and ultimately habitability is tied to climate and this problem of increasing climate. And so there's a tremendous amount of intersecting issues and problems that don't just have to do with the physical science aspect of this problem, but the social science and the humanities aspect of how this is going to impact human societies and cultures across the world. So one of the things that is important, I know that we're all not from the Northeast, but when we start thinking about how students connect with what this all means, one of the principal understandings of effective communication regarding putting this in terms that people can understand and connect with is, of course, talking about impacts associated with our local area. And so I'm just going to demonstrate how that works a little bit, walk through some of the risks associated with the Northeast. And what I'm going to show you actually draws a lot from the 4th National Climate Assessment. I'll cite it here, and it's in some of the materials at the end of my talk. But I encourage you all, regardless of where you're from in the US at least, to look at the National Climate Assessment, and there's a tremendous amount of material in the assessment that goes through how climate change will impact your specific area. But if we look at specifically the Northeast, one of the things that I think is particularly useful for thinking about this problem, if we think about the tri-state area here in the Northeast, and we think about those projections that I showed you, this figure on the left, I think puts it in a useful context. So what it's showing is how, with the increase of temperatures and the climate changes associated with that, this tri-state area will actually move south in the characteristics of its mean climate. And if we actually look at that worst case scenario, the climate in the tri-state area is projected to be something more like South Carolina or Georgia by the end of the century. And I've included a picture of, for those of us unfamiliar with South Carolina, or if you haven't been there, this is a picture of a forest in South Carolina showing its native inhabitants, a couple alligators and a turtle. But just to put that kind of a climate change in context, imagine those kinds of conditions being more representative of the Northeast. The projections in things like temperature and precipitation from the National Climate Assessment project that for the Northeast will increase precipitation by about 1 inch. We in this area will expect more severe downpours and really increased precipitation through the century. And we expect the region to warm by as much as 2 degrees Celsius or 3.6 degrees Fahrenheit. So it's going to get warmer and wetter in this region, and that has implications. We can expect more heat waves like the one that we're experiencing in the Northeast right now, and hopefully we'll be wrapping up over the next 24 hours. Heat waves are associated with more hospital visits, more mortality, particularly in vulnerable populations associated with heat exposure. So that's something that's also true of many different regions that are going to warm over this century. It's not just the air that's warming, as I mentioned, the seas are warming as well, and that's important for the animals that live in the ocean. And it's important for our economy because, particularly in the Northeast, for instance, it's tied to the fishing industry. Lobster and cod and sea bass are all important commodities that feed the East Coast commodities market in a lot of different ways. And as a consequence of the warming seas, some of the species are moving out of this area, and other species are moving in. Some are dying off just because the warmer temperatures are outside of their ideal range. So it's not just the air that's warming, and there are consequences in the ocean as well. This is one of my least favorite ones. If you live in the Northeast, you're familiar with Lyme disease and West Nile virus. As climate changes, the range and the time during which vectors like ticks and mosquitoes are active increases. And one of the features of climate change over this century will be to increase the range and the life cycle of ticks and mosquitoes, also bring new mosquito species into the area that carry diseases. And as a consequence, things like Lyme disease and West Nile virus will increase in the area. So public health concerns associated with this. If you were here during Hurricane Sandy, you know what that was like. Climate change is expected to make storms stronger and wetter as they come into our area, and we've already seen the kind of drastic impacts on our infrastructure that those kinds of storms can have. Those storms will also be happening over seas that are rising. So we've had about 6 inches of sea level rise in roughly the last 50 years. We will see another 6 inches of sea level rise, specifically in the Northeast area, by 2031. So significant amounts of sea level increases. The global sea level rise, depending on the scenario, but for that worst case scenario, is projected to be about 1 meter of sea level rise globally. So lots of things about sea level rise that imperil infrastructure. As storms come through and cause storm surges, those storm surges are operating on top of already higher sea level rises. And for a lot of our infrastructure, a few inches can make a difference. For instance, if you were here and saw South Street Seaport, it was really just a matter of feet that made the difference between otherwise having been okay. And so this is a serious feature that threatens our infrastructure as well. The other point that I want to make about this that is an important one and one that we're learning more and more about is the climate justice that sits under all of this. So this is a figure showing the damage relative to county income in the United States. So this was done in county by county in the United States. The horizontal axis is the wealth of the US counties that were analyzed. So the poorest counties are on the left, increasing to the richest counties on the right. And what this shows is that the poorer communities suffer larger economic damages as a consequence of the projected risks in the future. And what's interesting about this is that it scales across all spatial scales. So it's true in a community like New York City, our poorer, more vulnerable populations are being impacted by the changes that are already taking place and will be more impacted going forward. And it's true at the state level, at the federal level, at the international level, that the impacts of climate change will be borne most significantly by our more vulnerable communities. So there's a huge climate justice question and that sits underneath all of this. And again, really ties in climate change to all of these other features of our societies and our history and the context that has created these kinds of disparities within our culture and our world. Okay, this is all rather depressing, but I do like to point out with a couple dated cultural analogies to help put this in context. So the first thing I like to point out comes from a cartoon I used to watch when I was younger, G.I. Joe. It would always end with knowing is half the battle. And I think an important thing to keep in mind as we educate ourselves about this problem is that knowing really is fundamental to motivating action. So we have to learn about this. We have to learn about the risks that we're confronted with to really create the most sensible path forward, to teach us what needs to be done and what we need to be thinking about. The other dated cultural reference is Austin Powers. Some of you may remember this scene from the movie where the security guard stands here in the path of Austin Powers on a steamroller. He's screaming his head off. We think that his demise is imminent, but as we pan out, we realize that the steamroller is moving very, very slowly and he has ample time to get out of the way. He doesn't. I like to think about this as an analogy for climate change. It's a slow, chronic risk, and it's incumbent on us to simply get out of the way, to think about how to prepare for this risk this chronic, slow, imminent risk in a way that will keep us safe and mitigate the worst risks that we face into the future. So we shouldn't be the security guard. We should be actively thinking about how we can all pick up the tools that are unique to each of us and help us address this coming problem. So I'm running out of time a little bit, but I want to make a few more points along the lines of how I see so many things connecting with this and the opportunity for engaging students on these issues. It's not all doom and gloom. There's a lot of exciting solutions to climate change that can be pursued. There is, and there's some really good news. This is showing the cost of different energies over the last roughly 10 years. And what it's showing is that utility scale solar and wind are beating out all other energy sources currently by price. And that has huge implications for how these energies will be adopted into the future. We also know that in the United States specifically, perhaps reflecting those price changes, that renewables are increasing and things like coal are decreasing. So this is the use of coal decreasing significantly over the last decade. You can see that natural gas, which some talk about as transition fuel, has gone up, which has fueled some of our greenhouse gas reductions, but also the increases in renewables has been important. You may not know this, but we actually are reducing our emissions in the United States. Part of that is through our adoption of the more greenhouse gas efficient natural gas, but it's also because of the renewable increases. And so if you look in the shaded blue, the lighter blue, that's the Copenhagen Accord and Paris Agreement targets. And we've been up and down and we'll see where we go from here. But in terms of meeting those targets and being at least on a downward trajectory, the United States is doing okay. This isn't true of the world, of course, and that story is very important. But within the United States, it's important to keep in mind that there is some good news in terms of where we're going. We also have technologies for taking carbon out of the atmosphere. This is the first commercial carbon capture project outside of Zurich, Switzerland. These machines here are actually passively removing carbon dioxide from the atmosphere. And that carbon dioxide is then being used to fertilize plants in these greenhouses in the background. It's nowhere near the kind of scale that we need, but these technologies exist and are important moving forward for how we can address this problem. There are other projects like this where we're actually sequestering carbon in the geologic formations under the sea. So this is the Sleipner project, which has been active since the late 1990s. And again, 17 megatons of CO2 may sound like a lot. It's not in terms of our annual emissions, which are in the 30s of gigatons, but it is a demonstration of how we can address these problems moving forward and how the technologies exist. I'm going to end on this. Well, I'm going to show you one more slide after this, but one of the things about engaging students on this problem is, and one of the things that I find in teaching sustainable development is that the power and I think the engagement of this isn't so much about where we've been, but the excitement of reimagining what the future might look like. And that's where I think a lot of students connect with this problem. We can really reimagine the future in any way that we want. We can put our heads in the sand and just kind of keep moving forward as we are, or think hard about how we want our future to look and what kinds of technologies we might adopt into the future in a way that I think is really engaging for a lot of students as they think about this problem. I am going to skip over a lot of stuff, and perhaps as just a way of motivating some discussion, I want to put this up. Perhaps you've seen it. This is a poll from NPR about teachers who teach about climate change or why they don't. So the poll found that 8 in 10 teachers and a similar majority of parents support teaching kids about climate change, but in practice, fewer than half of teachers actually talk about climate change, and the rough percentage of parents does the same. The primary response for why teachers don't teach this subject is because they don't think it's related to the subjects that they teach, or that third down the list is that they don't know enough about it. I would say you're all working to educate yourself through activities like this to learn more about it. And I think that there's a tremendous amount of material to engage out there, to educate yourselves about this problem. And I hope that in some of what I've shown you, it's also true, and you can see that there's a tremendous ways in which this problem intersects with just about everything that we teach. Climate and its impacts are connected to so many different social science and humanities factors, of course, the physical science that sits behind it. But I think that you'll find as you begin to explore this subject in more detail, that there's tremendous opportunity for connecting it to whatever it is that you're teaching. And we're certainly finding that at the university level as we think more and more about how this issue pervades so many different things about how we live and operate on this planet. So perhaps this poll rings true for you. Maybe you see something in it that is representative of your peers or how you're thinking about it. But I'd love to talk more about this if you have thoughts about it and anything else that I've raised in the context of this presentation. Thanks very much.